Hi, this is Mr. Ward. I'm going to talk about problems from problem set B in chapter 10.4. And we're going to start with number 10. The centers of two circles have radii 10 and 5 are 13 centimeters apart. We're going to find the length of the common external tangent, and you're going to use the common tangent procedure that I discussed in an earlier video and which is in the sample problems. Now, question B is actually useful to consider in this one before you start dealing with it because you're going to have to draw these. So I'm going to pause and draw what we have. You should consider what it's going to be. You should try drawing it and see if you get something similar. Okay, I've drawn our two circles, not really to scale, but here's what we know. Their radii are 10 and 5, which means their combined radii would be 15, but their centers are 13 apart, so they must be closer than 15. So they're going to be intersecting rather than disjoint. Disjoint would mean they don't touch. So they're intersecting circles. So they have this overlap. And the distance between their centers is 13. So we can draw a center segment for the two circles. I've also drawn the radius here and the radius here. And because I drew those to the centers of the lines of the common tangent, those are right angles here. Okay. Now, what we're going to do is we're going to go ahead and follow the common tangent procedure. And I realize that those don't look like right angles, but based on the information, we're going to consider them right angles. So go ahead and see if you can figure this out, what to do. I've already done the first couple of steps of the common tangent procedure. I assume you paused. You want to refer to it, though. But if you pause and you're back, I drew the segment of the centers. I drew the radii to the points of contact. I, of course, drew the common tangent. And so what I'm going to now do, this is a variation, I'm going to actually draw a right triangle here. Now, I know that this side is 13. I know that this radius is 10, so this side is 5. Okay, so I've got 5 and I've got 13. And then this 13 is the hypotenuse because this is a right angle to the radius here. So I've got a 5, 12, 13 right triangle. So the distance, the length of the common external tangent segment is 12 units, 12 centimeters, they've told us. All right, let's go on to number 11. And by the way, I would say if I had this to do again, I would draw this bigger and make it a little more obvious what the right angles are. But the right angles are going to be where the radius comes in contact with the point of tangency. So I would encourage you giving yourself a little more space than I gave myself for this drawing. Number 11, the centers of two circles with radii 3 and 5 are 10 units apart. You want to use the length of a common internal tangent, or you want to find the length of a common internal tangent. We're going to try doing the same thing again. You're going to have to draw this. I'm going to pause while I draw, and I'm probably going to blow this up a little so I have more room. Okay, I have drawn this, and we know some things. We know this is 3, and we know this is 5, and we know this length here is 10. And because the radii are 3 and 5, we know the circles are disjoint. They're not intersecting, so there's a little space between them. And here's our line, our common internal tangent between them. So it's internal because it's between them. So we're going to do a variation of the common tangent procedure. If you recall, one of the steps of the common tangent procedure after you drew the segment of the centers and the radii to the points of contact, which of course make right angles, is to, through the center of the smaller triangle, draw a line parallel to the common tangent. Well, this is going to look different from this one in the example, but that's what you're going to need to do. Here is the common internal tangent. Pause the video and see what you can do. Assume you paused. I'm going to draw it now. So, okay. Now, because that's parallel, I know that I could extend this, okay? And this makes a rectangle. And that's a right angle right there because it's parallel to this. And so I know some stuff. I've made a right triangle. And I've made a right triangle where the base is equal, it's the opposite side of the common internal tangent. So I can use a Pythagorean theorem to find what that is. Okay, so I know that the hypotenuse is 10. I know that this side is 5 plus the radius of the smaller circle, because the radius of the smaller circle is the opposite side of this thing that is supposed to be a rectangle. I know it doesn't quite look like one, but it is a rectangle, I assert so. So we've got a side here that's 8, a side here that's 10, that's the hypotenuse, and you can use Pythagorean triples to figure out that x is going to have to be 6 in this case, because it's a 6, 8, 10 right triangle. All right, let's go on to number 10. Given PT is tangent to circles Q and R at points S and T, and we need to prove this proportion that PQ is to PR as SQ is to TR, as the radii are to each other. All right, I'm going to encourage you to pause the video, but you notice we've got a proportion, so it's likely we're going to be trying to prove some similar triangles. Okay, assume you paused, and let's go ahead and figure some things out. Well, for one thing, we can look, what we want to look at is triangles PSQ and PTR. And what's very convenient is we have right angles here and here, and this angle is itself. And by no choice theorem, then we have these two sides. Actually, we don't even need no choice, these two angles. We don't even need no choice. Angle gives us similar triangles. So we know that PSQ and PTR are similar triangles, and so their corresponding sides will form proportions. So PS is corresponding to, I'm sorry, not PS, let me undo that. PQ is what I want. PQ corresponds to PR, and SQ corresponds to TR. So we can set up a proportion of PQ is to PR, so PQ is to PR as SQ is to TR by similar triangles. We're going to do this walk around problem now, which is number 13. We got 3 tangent circles. That means they touch at one point here, here, and here, A, B, and C. And we know the radii of the 3 circles. And so we are going to try to find, we know the distances between the centers. We know the segments of the centers. Back up, we don't know the radii. We're trying to find the radii of the 3 circles. Find that radii, those radii. So pause and see what you can figure out. Well, I'm going to pause and I'm going to label some things. Okay, you could have labeled this a little bit differently than I did. I chose to treat circle C's radius as x, and the distance between AC is 11 minus x, since AC is 11. Since I got the radius of A being 11 minus x there, this will also be 11 minus x. And since AB is 8, I treated the radius of B as 8 minus 11 minus x. And then I know that BC is 13, so I treated the radius of B here as 13 minus x. And what I was trying to get was two different expressions for the same radius, so that I could say this, that those are equal. And now I can solve that. And I'll let you consider how to solve that. Pause the video. I'm going to pause and write it all out so you don't have to wait for me to handwrite all this. Okay, so we've got this structure here. 8 minus 11 minus the difference of 11 minus x, so that's 8 minus 11 plus x here. And that's going to be negative 3. Negative 3 plus x. I'm going to add 3 to both sides to get rid of the negative 3 on the left. And that's going to be 16 minus x equals x. I'm going to add x to both sides to get that. And now I've got 2x equals 16, so x has to be 8. So that tells me that this piece here, the radius of C is 8. And since BC is 13, the radius of B needs to be 5. 8 plus 5 is 13. And I've got 11 minus x, and that's 11 minus 8. The radius of A has to be 3. So let me put all that in. So this equals 8. This one has to be 11 minus 8, so that's 3. And this one has to be 13 minus 8, so that's 5. And you notice they're not drawn to scale. That probably messes with some of your universes, but I'm afraid we got to deal with it. And I appreciate it. I feel your pain. So number 14, the radius of circle O is 10. And the secant segment PX measures 21 and is 8 units from the center of the circle. So we want to find the external part of PY to the secant, and we want to find the distance OP from point P to the center of the circle. So you might infer that we're going to be dealing with some Pythagorean Theorem stuff here, and you would be right. So go ahead and pause the video and see what you can come up with. I'm going to label some stuff. All right, so hopefully you've done some labeling of your own. I have noted that the distance to the secant from the center is 8. I've drawn a radius here from O to X, and I know the radius is 10. I'm going to work out and I've labeled these two pieces X because they have to be congruent, because this XY is a chord that is perpendicular to OZ, and that's the distance from center. So we've got a chord theorem that we can work with. This is a bisected chord. So we can figure out X by using a Pythagorean theorem, and hopefully you have already noticed that X has to be 6. Okay, which means this is 6. Which means we know what this part is too, because 6 plus something is 21, and then we'll have a side of another right triangle. Pause and see if we can work out what YP is going to be. I'll assume you have done so. And so since this is 21 minus 6 or minus 12, YP is 9. So ZP is 15. So we have a right triangle with 8 and 15, and 17 is the distance to the center of the circle. So PY is 9, OP is 17, and you're done with that. I'm going to stop this video and go on to some harder stuff.